Hi, I'm Liz Rice. I am Chief Open Source Officer at Isovalent, which is the company that originally created the Cilium networking project. Cilium is now part of the CNCF, and it uses technology called eBPF that I'm sure you've come across already before. So I'm not going to talk too much about the basics of eBPF, but today I'm going to talk about how we use it to create really high performance networking for Kubernetes and other distributed systems. So a little bit about my background. You may have come across me perhaps through the work I've done with the CNCF. I was chair of the Technical Oversight Committee until earlier this year. I've also written a book about container security. I've in progress on a book about eBPF, and I've written a short report called What is eBPF that you can download from the Isovalent site should you wish to get that background on what eBPF is. Now, before I got involved in containers and security and eBPF, I actually had quite a long background writing networking protocol stacks. So coming back to the Cilium project and Isovalent was a bit like a return to my roots. So it's been really great to get involved with seeing how networking has improved over the years and how we can use eBPF to really improve that performance. One of the technologies that we take advantage of in Cilium and in other eBPF-based networking solutions is something called XDP. It stands for Express Data Path. And it's a way of using eBPF programs really early on in the path of a network packet's journey into the computer. Now, I'm told by one of my colleagues that the idea came from a conversation which almost flippantly said, wouldn't it be great if we could run eBPF programs on the network interface card? And in fact, you can do that today. There are network interface cards that support XDP, Express Data Path, and allow you to offload your eBPF programs onto the NIC hardware so that as a packet arrives, it can trigger that eBPF program and be processed by that program on the NIC itself. So if your program does something like discard that packet, it never gets as far as the kernel's networking stack at all. So this can be a really high performance way of handling packets. Not all network cards support XDP hardware offload, but in other circumstances, we hook to an XDP point as close as possible to the packet arriving on that physical network connection. One place this has been used really effectively is for mitigating vulnerabilities called packet of death. So the idea of a packet of death vulnerability is that there's a bug in the kernel, in the networking stack somewhere, where a particular format of network packet, particularly crafted network packet, isn't handled correctly. So it's a bug in the kernel that means if you've formed a packet in this particular way, the kernel's going to crash. So an attacker will deliberately send packets formatted as packet of death to try to bring machines down. With XDP, we can inspect those packets, look to see if they are packets of death, and discard them really quickly and efficiently. And of course, if you have a network card where you can offload to hardware, you can do that before the packet even gets to the host itself. The real beauty of this is that because it's eBPF, it can be loaded dynamically. You don't have to install a kernel patch, you don't have to reboot your machines. You can install these mitigations live and dynamically. So as an example of code that would drop packets like this, I want to show a little demo that will deliberately drop ICMP packets, also known as ping. So I have a little XDP program here. Don't need to worry too much about what's happening here. We're looking at the packet and trying to figure out what protocol it is. And at the moment, I'm just going to trace out if I get a ping packet, I'm going to say it's ICMP. If I see a TCP packet, I'll say it's a TCP packet. And I have a container. I'm going to install this XDP, or I'm going to install this eBPF program onto the XDP interface for packets coming into this container. So if I look at my IP address here, this is my F0 interface, and here is the IP address. And I can start pinging that IP address from outside, and I'm starting to get responses. I'm also just going to trace out kernel debugging tracing, which will show these messages when they're triggered. So if I run, I've got a make command that will compile my eBPF program and load it onto the interface. So we can see it being loaded here and then attached to the XDP interface. And in fact, if I look at the interface again, we can see the program loaded here. And you probably already noticed that the tracing has started generating messages for every ping that's been received. So now I'm going to change the program, and instead of passing ICMP packets up the stack, I'm going to drop them. So that means every ICMP packet that's received across that F0 interface into the container is just going to be discarded. So if I run make again, it's going to remove the existing program, compile the new one, and install it. And what we can see is the tracing is still continuing because we're still hitting this line here, but the sequence numbers for the ping messages are no longer incrementing. My client outside the container is sending ping messages, but it's just not getting any response because the request never makes it into the container. And just to prove that it wasn't the act of removing the program or something, I'm just going to turn it back on again, recompile, and we can immediately see the pings are starting to be received again. So that's an illustration of how we can use eBPF to dynamically change the behavior of networking in a system. We don't just use it for discarding packets. We also have the opportunity with XDP to manipulate those packets. We can change, for example, the source and destination addresses that are contained within those packets. And one application of this that's very popular is load balancing. So a packet can arrive, be processed by an eBPF XDP program, which determines what destination to send that packet to, which of a range of backends. And that could be on that host, or perhaps it's on a different machine altogether, in which case XDP can send the packet back out through the interface. It never gets processed by the kernel's networking stack. And the fact that this happens so efficiently leads to real performance gains. Seznam, a company from the Czech Republic, wrote a really great blog post about their experience using Cilium in its standalone layer 4 load balancer configuration. So they have been experimenting with running that XDP-based load balancer versus an IPVS-based load balancer, and they saw dramatically better throughput, over twice as good throughput with the XDP version. There's also some more details in that blog post about how it reduced CPU usage. Now, XDP is by far not the only place that we can attach eBPF programs to in the network stack. You probably know we can attach eBPF programs essentially anywhere across the whole kernel. You might have seen tracing and profiling programs and utilities, perhaps the work that Brendan Gregg did with BPF Trace, to use eBPF all across the system to get really detailed profiling and tracing information. And we can attach eBPF programs to many other places in the network stack to manipulate those network packets and perhaps redirect them and avoid parts of the kernel's native networking stack. And the reason why we might want to do this is because the networking stack can be really quite complex. In Kubernetes, not only do we have a networking stack on the host, but we deliberately isolate each pod. Our applications all run in their own independent pods, and those pods have their own networking namespace, and that means a separate instance of the networking stack is run for each pod. So an incoming packet from the outside world arrives at the host, has to pass through this very convoluted route to get to the virtual Ethernet connection that then transports the packet into the pod's namespace, where again it traverses this really complex networking stack to reach the application. And a whole lot of this processing is related to IP tables and contract. So one of the things that Cilium does very effectively is to look at how we can bypass as much of this IP tables and contract as possible. Not only is the route for each packet very convoluted and long through this IP table stack, in Kubernetes, IP tables rules get used a lot. So for each pod, there will be rules routing packets to that pod, but where pods are grouped into services, there will be additional rules used to load balance traffic across all the pods that make up that service. Whenever you change an address, when a pod gets created or destroyed, that requires changes to the IP tables, and all these rules have to be rewritten. So that's potentially quite a lot of processing. Even outside of a Kubernetes environment, simply routing through that convoluted network stack does take quite a lot of CPU cycles. This was some performance data taken from simply container networking between some Docker containers with no Kubernetes involved. And you can see that quite a significant amount of CPU was being used in IP tables and contract. So, as I said, with Cilium, we want to bypass as much of this as possible. And we can do that by hooking eBPF programs in at a variety of different points in the network stack. And this allows us to bypass a huge amount of that processing. Essentially, an incoming packet can be brought into Cilium and directed into the virtual Ethernet connection for the pod directly. We can see in a flame graph that the amount of processing required is reduced. We can see here a certain amount of time being spent in eBPF processing, and then the packet being sent directly into the TCP/IP stack for the pod. Not only do we get the opportunity here to bypass parts of the stack and route these packets appropriately, we also have the opportunity to do security policy checks. We can drop packets, just like you saw with the XDP example. We can drop packets if they don't meet security policies, those security policies dictating which pods are allowed to communicate with which other pods or which other external endpoints. And we can use eBPF to provide that load balancing. So instead of using IP tables rules to load balance traffic across all the pods that make up a service, we can implement that in eBPF. And that's one of the things that we do in Cilium. We can use that to replace the kubeproxy component entirely. So essentially, you can delete your kubeproxy deployment. Let me show you a demo to prove that that's possible. So I have a Kubernetes cluster here. It's running in kind just for illustrative purposes. And I have 3 pods here, and they back a service called Echo Server. And if I send a curl request to that service, actually need to type in the word curl, that will help. Then we get a response back that tells us which of the pods has responded. And we should see if I send a few requests, they come from, or they're handled by different pods. So the requests are being load balanced across those 3 pods. Now, if I just go back to showing where they're all running on this worker node, and I'm going to just exec into the container that's running that. Kind worker, and I'm going to run a bash shell here. And here I can look at the IP tables rules that are currently on that node. And there are quite a lot of them. If we scroll up, here is the part that the chain that does the load balancing across those different Echo Server backend pods. We can see the IP addresses here, 195, 217, and 22, which match what we have here. So another thing we can do with this IP tables is we can actually see the count of bytes and packets that are being processed by those tables. And I'm just going to grep out the ones that are related to Echo Server. So every 2 seconds, this is going to be updated, and we can see the number of packets on the left and then the number of bytes that have been handled by these different rules. And if I send some curl requests, we should see, you can see them being highlighted as those numbers are changing. So that's proving that traffic is being handled by those rules. Now, if I look at the Cilium config at the moment, need to view it, and we scroll up to kubeproxy replacement, we can see that at the moment kubeproxy replacement is disabled. So I'm going to change that to enable kubeproxy replacement. Replacement strict. Now that is restarting the Cilium pods, only the Cilium agents. The application pods are still running. They're identical to, well, they just haven't changed at all. And while the Cilium agent is restarting, the eBPF programs are left in place. So traffic can continue to flow regardless of the fact that Cilium agents may be temporarily unavailable. So it can take a moment or two for the change to take place, but hopefully I've spoken for long enough that if I start issuing curl requests, they're still fulfilled correctly, but we're not seeing any changes now in that top screen. So these requests are still being load balanced across the different pods that make up that service, but they're no longer being handled by those IP table rules. So effectively, we've been able to bypass that whole part of the stack. And as I say, we could delete the kubeproxy components altogether. This has real impact on performance. We've actually implemented this a couple of different ways. One time using, or the most recent time, using XDP. And as you can see, that's dramatically more throughput than even the TC-based implementation, which in turn was significantly faster than the kubeproxy implementation based on IP tables or on IPVS. Not only is the throughput faster, but it frees up CPU usage so that you can use that CPU for your applications rather than for networking. So in this graph, higher is better because it's more available CPU. So I hope that illustrates how we're using eBPF in Cilium to provide high performance ways of bypassing parts of the network stack and create some real improvements in throughput, free up CPU usage, and make your Kubernetes systems more efficient. If you're interested in learning more about eBPF, there is a community site, ebpf.io, and of course there is the Cilium project website, cilium.io. I am available pretty much everywhere on the internet as Liz Rice, so please do feel free to reach out to me on Twitter or in the Cilium Slack if you have questions. Thank you.